Look up at the night sky. What you see is a beautiful lie. Those pinpricks of light, those familiar constellations, appear fixed and eternal, a comforting constant in our lives. But the reality is far more dynamic and, frankly, far more astonishing. What if I told you that the very fabric of space itself is stretching, right now, carrying entire galaxies away from us at speeds that defy imagination? This isn't science fiction. This is the cornerstone of modern cosmology. We are living inside an expanding universe, a concept so profound it completely rewrites our understanding of reality. It means the cosmos is not a static stage but a living, breathing entity growing larger with every passing second. And this single, incredible idea is the key that unlocks secrets about our past, our future, and our ultimate place in the grand scheme of things. This journey of cosmic discovery began less than a century ago with a monumental revelation. In the 1920s, an astronomer named Edwin Hubble made an observation that would shatter humanity's static view of the cosmos forever. By carefully studying the light from distant galaxies, he noticed something peculiar. Their light was stretched, shifted toward the red end of the spectrum. This redshift was the telltale signature of motion away from us. But the real shock wasn't just that galaxies were moving. It was that the farther away a galaxy was, the faster it appeared to be receding. It was as if space itself was the thing expanding, like dots on an inflating balloon, each dot moving away from all the others. This discovery of the expanding universe was a paradigm shift of the highest order, placing us not at the center of a stable creation, but on a tiny fragment of a vast, evolving cosmos. Today, we stand on the shoulders of those giants, armed with powerful telescopes and deep curiosity, ready to explore the astounding implications of this expansion. In this video, we are going to embark on a journey through 25 of the most mind-bending facts about our expanding universe. We will grapple with concepts that challenge our very perception of time and space, from the possibility of a multiverse to the mysterious dark energy that seems to be pushing the expansion to ever-increasing speeds. We will explore what this means for the ultimate fate of everything we know. This is not just a list of facts, it is an invitation to expand your own mind, to feel the awe and wonder that comes from confronting the true scale and nature of existence. So, let's begin our voyage into the deep unknown, where every answer reveals a new, more profound question. Edwin Hubble's monumental discovery began with a seemingly simple observation. Peering through the massive Hooker telescope at Mount Wilson Observatory, he was studying faint, fuzzy objects then known as spiral nebulae. The prevailing belief was that these were simply clouds of gas within our own Milky Way galaxy. But Hubble identified individual stars within the Andromeda Nebula, proving it was an entire galaxy, a vast island of stars far beyond our own. This alone redefined our cosmic address, showing the Milky Way was just one among countless others. But the real revolution was yet to come. By analyzing the light from these galaxies, Hubble noticed a consistent and startling pattern. The light from almost every galaxy he observed was shifted toward the red end of the spectrum. This phenomenon, called redshift, is akin to the Doppler effect for sound. Just as a receding ambulance siren sounds lower in pitch, the light from a receding object is stretched to longer, redder wavelengths. The inescapable conclusion was that these galaxies were all racing away from us. Yet the true genius of Hubble's work lay in what he did next. He combined these redshift measurements with estimates of the distances to these galaxies. The correlation he uncovered was both simple and earth-shattering. The farther away a galaxy was, the greater its redshift, and therefore the faster it was moving away. This relationship is now enshrined as Hubble's law, often written as velocity equals Hubble's constant times distance. This wasn't just a description of galaxies fleeing from us in particular. Imagine a loaf of raisin bread baking in the oven. As the dough expands, every raisin moves away from every other raisin. A raisin on one side of the loaf sees all other raisins receding, and the ones twice as far away appear to move twice as fast. Our galaxy is just one raisin in this cosmic loaf. The space between the galaxies itself is stretching, carrying them apart. This single observation was the first direct observational evidence that our universe is dynamic and evolving. It completely overturned the ancient idea of a static, unchanging cosmos. If we could rewind this expansion like a film in reverse, all that space between galaxies would shrink. The galaxies would get closer and closer together until eventually the entire observable universe would be compressed into an incredibly hot, dense state. This brilliant flash of logic directly points back to a beginning, a moment of creation we now call the Big Bang. Hubble's discovery of the expanding universe provided the first crucial piece of evidence for this grand theory, setting the stage for a century of cosmic exploration that continues to challenge our deepest understandings of reality. And this leads us directly to our second astounding fact, one that corrects a common misunderstanding about the nature of the cosmos. When we hear that galaxies are moving away from us, it's natural to picture them rocketing through the void like ships sailing across an empty ocean. But that mental picture is fundamentally incorrect. The reality is far stranger. The galaxies themselves aren't necessarily traveling at incredible speeds through a stationary space. Instead, it is the very fabric of space itself that is stretching and growing, carrying the galaxies along with it. Think of it not as objects moving through space, but as space itself expanding between the objects. This distinction is absolutely crucial, as it changes everything about how we perceive the mechanics of the universe. The most effective way to visualize this is with the classic analogy of a loaf of raisin bread baking in an oven. Imagine the unbaked dough represents the fabric of space. The raisins scattered throughout the dough are the galaxies. Now, as the bread bakes, the entire loaf expands. The dough itself stretches in all directions. What happens to the raisins? Each raisin remains stuck in its own local patch of dough. It doesn't travel through the dough. But as the dough expands, the distance between every single raisin increases. From the perspective of any one raisin, all the other raisins are moving away. And here's the key point that mirrors Hubble's law. A raisin that was initially twice as far away will find that the amount of dough between it and you is also twice as much, so it will appear to recede at twice the speed. The expansion is uniform, it's happening everywhere at once. This analogy perfectly captures the essence of cosmic expansion. The raisins aren't propelling themselves, they are passive passengers on a stretching landscape. This explains why more distant galaxies recede faster. There is simply more expanding space between us and them. It also resolves a potential paradox. If galaxies were just flying apart from a central point, we might expect to be at the center of that explosion. But with the expanding space model, every galaxy, every raisin sees the same thing, all the others moving away. There is no center to the expansion. The center is everywhere or perhaps nowhere at all. This concept also helps us understand a truly mind-bending consequence. Because it is space that is stretching, the expansion is not limited by the speed of light in the way that objects moving through space are. Two galaxies can be carried apart by the stretching of space between them at an effective speed that is greater than the speed of light. This doesn't violate Einstein's laws because no information or matter is actually traveling faster than light through space. The space itself is just becoming more spacious. This is why we can observe galaxies whose light has been traveling for billions of years, yet the space between us has stretched so much that they are now forever beyond our observable horizon. The universe isn't just getting bigger, the rules of the game are being rewritten by the expansion of the stage itself. For decades after Hubble's discovery, astronomers assumed they understood the basic fate of the universe. The cosmic expansion was a relic of the Big Bang's initial push, a colossal explosion that sent everything flying apart. But gravity, the great cosmic architect, was always there, acting as a constant brake on this outward motion. The central question was one of sheer power. Was the initial impulse of the Big Bang strong enough for the universe to expand forever, gradually slowing down but never stopping? Or was gravity's pull ultimately victorious, destined to eventually halt the expansion and pull everything back together in a catastrophic big crunch? This was the great cosmic tug-of-war, and for most of the 20th century, scientists were meticulously measuring the expansion rate, trying to determine which force would win. The prevailing expectation was that gravity would be slowing the expansion down. The only real mystery was by how much. Then, in the late 1990s, two independent teams of astronomers set out to make the most precise measurements of this cosmic deceleration ever attempted. Their tool was a specific type of stellar explosion known as a Type 1, a supernova. These supernovae are extraordinary because they all explode with nearly the same intrinsic peak brightness. This makes them what astronomers call standard candles. If you know how bright something truly is, you can measure how bright it appears from Earth and accurately calculate its distance. By looking at extremely distant and therefore ancient Type 1 supernova, these teams were essentially looking back in time, measuring the expansion rate of the universe billions of years ago. They planned to compare this ancient rate to the more recent one to see exactly how much gravity had slowed the cosmic expansion. What they found, however, was not a slowdown. It was the opposite. The distant, ancient supernovae were fainter than their models predicted. This meant they were farther away than they should have been if the universe had been expanding at a steady or decelerating rate. The only possible explanation was staggeringly counterintuitive. The expansion of the universe was not slowing down at all. Instead, it was speeding up. Some unknown force was acting against gravity, pushing galaxies apart at an ever-increasing rate. The universe's accelerator pedal was being pressed down. This discovery was so shocking and so contrary to all expectations that the researchers spent years double-checking, triple-checking, and searching for any possible error in their data or analysis. But the result held firm. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this revelation, which fundamentally reshaped our understanding of cosmic evolution. This accelerating expansion demands a cause, a mysterious something that exerts a repulsive force on the very fabric of space. Cosmologists call this something dark energy. The name itself reflects our profound ignorance. It is dark because it doesn't emit or interact with light in any way we can detect, and energy because it seems to be a property inherent to space itself. The leading theory suggests that dark energy is the manifestation of the cosmological constant, a term Albert Einstein originally inserted into his equations of general relativity to force a static universe, which he later called his greatest blunder after Hubble discovered the expansion. Ironically, it now appears Einstein may have been right for the wrong reason. This cosmological constant represents a constant energy density filling space homogeneously. As the universe expands and more space comes into existence, more of this repulsive energy appears, causing the expansion to accelerate faster and faster. Dark energy now appears to be the dominant component of our universe, making up about 68% of its total mass energy content. It is the prime driver of cosmic destiny, an invisible presence whose nature remains one of the greatest unsolved puzzles in all of science. So this discovery of an accelerating universe left scientists with a monumental question: what is pushing the cosmos apart? The leading candidate is one of the most enigmatic concepts in all of science: dark energy. It's important to understand that dark energy is not a substance in the way we normally think of things. It isn't a cloud of particles or a mysterious gas. Instead, the most widely accepted idea is that dark energy is a fundamental property of empty space itself. Think of a perfect vacuum, a volume containing absolutely nothing, no atoms, no light, no matter of any kind. According to classical physics, that void would be inert, but quantum physics suggests that even this empty space is not truly empty. It seethes with a faint background energy. This energy of the vacuum is what we call dark energy, and it has a bizarre characteristic. It creates a repulsive gravity, a kind of negative pressure that causes space to stretch. The true dominance of dark energy is almost difficult to comprehend. When we inventory the entire universe, the stuff that makes up you, me, the planets, and all the stars in all the galaxies, what we call normal baryonic matter, accounts for a mere 5% of the total cosmic budget. Another 27% is the equally mysterious dark matter, which exerts gravitational pull but doesn't interact with light. That leaves a staggering 68%. The majority of our universe is not made of any kind of matter at all, but of this repulsive energy inherent to the vacuum of space. Dark energy is the primary component of reality, the unseen ocean in which the islands of galaxies float. And as the universe expands, creating more space, more of this dark energy comes into existence, which in turn causes the expansion to accelerate further. It's a self-reinforcing cycle that grows stronger over time. Why does this remain such a profound puzzle? The challenge lies in the colossal mismatch between theory and observation. When physicists attempt to calculate the expected strength of this vacuum energy using quantum mechanics, they arrive at a number that is astonishingly large, about 120 orders of magnitude too large. That's a 1 followed by 120 zeros. This is often called the worst theoretical prediction in the history of physics. If the quantum calculation were correct, the repulsive force of dark energy would have been so immense in the early universe that it would have torn apart atoms before they could even form. Stars, galaxies, and life would have been impossible. Clearly, our understanding is incomplete. There must be some cancelling mechanism or a deeper principle we have yet to discover that makes the actual observed value of dark energy so much smaller, yet crucially not zero. This tiny but non-zero value is precisely what allows galaxies to form and life to emerge, raising the haunting question of whether our universe is uniquely tuned for our existence. The nature of dark energy is not just a technical problem, it is a gateway to potentially rewriting the most fundamental laws of physics. Building on that discovery of dark energy, we need a way to measure this acceleration precisely. This brings us to one of the most crucial numbers in all of cosmology, the Hubble Constant. Simply put, the Hubble Constant, often written as h0, is the current expansion rate of our universe. It tells us how fast the cosmos is stretching today. The concept is embedded right in Hubble's law. Velocity equals h0 times distance. The constant is the multiplier. It's the current speed limit, in a sense, for how much faster a galaxy recedes for every additional million light-years it is away from us. The units are a bit quirky: kilometers per second per megaparsec. A megaparsec is an astronomical unit of distance, about 3.26 million light-years. So, if the Hubble constant were 70 kilometers per second per megaparsec, it would mean that for every million light-years you look further out into space, a galaxy appears to be moving away from us 70 kilometers per second faster. Determining this number with high precision has been a monumental challenge for astronomers, akin to trying to measure the exact growth rate of that expanding raisin bred from the inside. You need to do two very difficult things with extreme accuracy: measure the distances to faraway galaxies and then measure their velocities via redshift. For decades, the uncertainty was large, but as our technology improved, from Hubble's original observations to the powerful Hubble Space Telescope that bears his name, the measurements became more and more refined. You would think that with our modern instruments we would have converged on a single, agreed-upon value, but that's where the story takes a fascinating and slightly troubling turn. Instead of converging, the measurements have revealed a persistent and significant discrepancy, a puzzle now famously known as the Hubble tension. This tension arises because we have two primary methods for measuring the Hubble constant, and they are giving us subtly but importantly different answers. The first method looks at the local or modern universe. Astronomers use incredibly reliable cosmic mile markers like the Cepheid variable stars and Type I, a supernova that revealed dark energy. They painstakingly measure the distances and velocities of these objects in galaxies relatively close to us to calculate the current expansion rate. This is like measuring the expansion of the loaf of bread by checking the distances between raisins right now. The second method looks back to the very beginning, to the early universe. This relies on the cosmic microwave background, the faint afterglow of the Big Bang, which was mapped in exquisite detail by satellites like Planck. This snapshot of the infant universe, when it was only 380,000 years old, allows cosmologists to run the cosmic film forward. By plugging the properties of this early universe into our standard model of cosmology, which includes dark energy and dark matter, we can predict what the expansion rate should be today. This is like measuring the initial ingredients and heat of the bread dough, and then using a perfect recipe to predict how much it should have expanded by the present time. The problem is this: the local measurements using supernova suggest a faster expansion rate. The early universe measurements using the cosmic microwave background predict a slightly slower one. The difference isn't huge, it's only a few percent, but given the incredible precision of both methods, that small gap is statistically significant. It's like two of the world's most accurate clocks, built by master craftsmen, ticking at stubbornly different rates. This Hubble tension has now persisted for over a decade, and as measurements have become even more precise, the discrepancy has refused to go away. This suggests it might not be an error but a clue. It could be pointing towards something profound that is missing from our standard model of cosmology. Perhaps dark energy is not constant but evolves over time. Maybe there are exotic types of neutrinos or other unknown particles influencing the expansion. Or it could hint at something even more revolutionary, like a flaw in our understanding of gravity itself. This isn't just a minor academic debate, it's a potential crack in the foundation of modern physics, a signal that our cosmic recipe book might need a crucial new ingredient. If the expansion of the universe points us back to a beginning, then the cosmic microwave background radiation is the ultimate piece of evidence, a fossilized echo of that creation event. This is a faint, cool glow of microwave radiation that uniformly permeates every single point in the sky, a cosmic hum that has been traveling for almost the entire age of the universe. It is quite literally the leftover heat from the Big Bang itself. To understand what it represents, we have to rewind the cosmic clock. In the very earliest moments, the universe was an unimaginably hot, dense soup of fundamental particles and energy. It was so dense that light could not travel freely. Photons of light were constantly bouncing off a thick fog of free electrons, trapped in a perpetual game of cosmic pinball. The universe was opaque, a brilliant, searing fireball. This continued for about 380,000 years. As the universe expanded, it also cooled. Eventually, it cooled enough for a monumental transition to occur. Electrons combined with protons to form the first stable atoms, primarily hydrogen. This event is called recombination. Suddenly, the fog lifted. With the electrons now bound inside atoms, the photons, which had been trapped for eons, were finally set free. They could stream across the universe unimpeded. The moment the universe became transparent, that first flash of light began its journey, and we can still detect it today. What we see as the cosmic microwave background is that very light, now greatly cooled and stretched by the subsequent 13.8 billion years of cosmic expansion. The initial brilliant, visible light flash has been redshifted all the way down into the microwave part of the spectrum. corresponding to a temperature of just about 2.7 degrees above absolute zero. It is the cooled-down ember of the cosmic firestorm. The story of its discovery is a classic tale of scientific serendipity. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were using a highly sensitive horn-shaped antenna to study radio waves from our galaxy. But they were plagued by a persistent, unexplained noise, a faint, uniform hiss that came from every direction in the sky, day and night, summer and winter. They meticulously checked for every possible source of interference. They even famously cleaned out a layer of pigeon droppings from the antenna, thinking it might be the cause, but the annoying hum remained. At the same time, a group of physicists at Princeton University, led by Robert Dicke, were actively building a detector to search for this very relic radiation, which they had predicted must exist if the Big Bang theory were correct. When Penzias and Wilson heard about the Princeton group's work, they realized they hadn't discovered an instrument defect. They had stumbled upon the afterglow of creation. Their accidental discovery earned them the Nobel Prize and provided the smoking gun evidence that solidified the Big Bang as the dominant model of cosmic origins. This background radiation is far more than just a uniform glow. It is the universe's baby picture. The tiny, minuscule variations in its temperature anisotropies that are only 1 part in 100,000 are the most important part. These fluctuations are like cosmic seeds. They represent regions of slightly higher and lower density in that early, smooth universe. The slightly denser spots had a little more gravitational pull, and over billions of years they attracted more and more matter. These seeds grew into the vast cosmic structures we see today, the clusters of galaxies, the galaxies themselves, and the stars within them. By studying the precise pattern of these temperature variations in the CMB, cosmologists can read the fundamental parameters of the universe, its age, its composition, and its geometry with incredible precision. It tells us that the universe is flat, that it is made of about 5% normal matter, 27% dark matter, and 68% dark energy, confirming the inventory we've discussed. The cosmic microwave background is therefore our most direct link to the infant cosmos, a snapshot from a time long before the first star ever shone. While the cosmic microwave background appears as a remarkably smooth veil across the sky, that perfect uniformity is an illusion when we look closely. When satellites like Planck mapped this radiation with extraordinary precision, they revealed a tapestry of incredibly subtle imperfections. These are temperature anisotropies, tiny variations where some patches of the sky are ever so slightly warmer or cooler than the average. We're talking about differences on the scale of 1 part in 100,000. To put that in perspective, if the CMB were an ocean, these fluctuations would be ripples no taller than a few centimeters. Yet, these minuscule ripples are arguably the most important features in the entire cosmos, for they are the primordial seeds from which the entire grand structure of the universe eventually grew. So, where did these fluctuations come from? Their origin lies in the quantum chaos of the universe's very first moments. In the fleeting instants after the Big Bang, the entire cosmos was subatomic in size. At this tiny scale, the rules of quantum mechanics reign, where uncertainty and random fluctuations are fundamental. Imagine a frothing sea of energy at the smallest possible scales. These quantum jitters, these random variations in density, were imprinted onto the fabric of the infant universe. Then, in a fraction of a second, a period of incredible expansion known as inflation is thought to have occurred. This inflation stretched the universe exponentially, magnifying those microscopic quantum fluctuations to astronomical sizes. What were once tiny, random wrinkles became the large-scale variations in density that were frozen into the cosmos by the time of recombination when the CMB was released. The hotspots in the background radiation correspond to those slightly denser regions where just a little bit more matter was concentrated. These tiny density differences became the universe's architectural blueprint. After the universe became transparent, gravity went to work. Regions with even a minuscule amount of extra mass had a slightly stronger gravitational pull. Over millions of years, this gravity acted like a cosmic amplifier, drawing in more and more surrounding matter, both the normal matter that makes up stars and planets, and the invisible dark matter that provides the gravitational scaffolding. The slightly denser patches grew denser still, evolving into vast cosmic webs of dark matter. Within these webs, normal gas cooled, collapsed, and ignited the first stars, gathering into the first galaxies. The slightly less dense regions, in contrast, evolved into the immense cosmic voids we see today, the great empty deserts between the walls and filaments of the galactic web. Every galaxy cluster, every spiral galaxy like our Milky Way, every star, and every planet exists because of the specific pattern of those ancient seeds. The pattern we see in the Planck satellite's map is a direct forecast of the cosmic structures that would emerge billions of years later. This connection makes the CMB more than just a relic, it is a Rosetta Stone for cosmology. By analyzing the precise statistical properties of these fluctuations, their size, their distribution across the sky, scientists can test our most fundamental theories about the universe's birth and composition. The pattern tells us that the universe is geometrically flat, which has profound implications for its overall shape and ultimate fate. It allows us to calculate the exact amounts of dark matter and dark energy with remarkable accuracy. It even provides evidence for the inflationary period that set the entire process in motion. In a very real sense, when we look at a map of the cosmic microwave background, we are reading our own cosmic ancestry. The specific arrangement of those hot and cold spots determined where our galaxy would one day form, and ultimately, the conditions that made our own existence possible. We are the heirs to a pattern of quantum noise, magnified across the cosmos and sculpted by gravity over billions of years. Now, those incredibly precise maps of the cosmic microwave background do more than just reveal the seeds of galaxies. They also allow us to answer a profound question about the shape of the cosmos itself. When we talk about the universe being flat, we're not referring to a two-dimensional pancake. Instead, it's a statement about the large-scale geometry of space-time, a concept from Einstein's theory of general relativity. Imagine drawing two perfectly parallel laser beams and sending them across the cosmos. In a universe with positive curvature, like the surface of a sphere, those parallel lines would eventually converge and cross. In a universe with negative curvature, like a saddle shape, they would diverge, spreading apart. But in a flat universe, those laser beams would remain perfectly parallel forever, exactly as the geometry we learned in high school, Euclidean geometry, would predict. This flat geometry has a very specific and critical implication. It means the total density of mass and energy in the universe is at a precise, golden value known as the critical density. The reason this is so significant is that the geometry of the universe is directly tied to its fate. For a long time, cosmologists described three possible outcomes based on this density. If the density were greater than the critical value, the positive curvature would mean gravity was strong enough to eventually halt the expansion and pull everything back together in a big crunch. If the density were less, the negative curvature would lead to a big freeze, where expansion continues forever but slows to a crawl, with the universe becoming cold and dark. The flat universe, balanced exactly at the critical density, was thought to be a perfect but unstable equilibrium, like a coin standing on its edge, destined to eventually tip one way or the other. But that was before the discovery of dark energy. Today, we know our universe is flat, yet its expansion is accelerating. This changes the interpretation completely. The flat geometry doesn't mean the expansion will slow to a halt. It means the total energy content is just right to create this specific geometric reality. The presence of dark energy ensures that this flat universe will expand forever and at an ever-increasing rate, leading to a fate far more dramatic than a simple freeze. So, how can we possibly measure the shape of something we are inside of? The answer, once again, lies in the patterns of the cosmic microwave background. The tiny temperature fluctuations we see have a characteristic size known as the acoustic peak. This scale is determined by how far sound waves could travel in the plasma of the early universe before it became transparent. Think of it as a fundamental cosmic ruler. When we look at the CMB, we are seeing an image of these ripples projected onto the sky. The apparent size of these ripples as we see them today depends entirely on the geometry of the intervening space. If space were positively curved like a ball, the light paths would be bent, making the ripples appear larger to us. If space were negatively curved, the light paths would spread out, making the ripples seem smaller. The detailed measurements from the Planck satellite show that the ripples appear exactly the size we would expect if the universe were geometrically flat. The light has traveled in straight lines across billions of light years without being bent or stretched by an overall curvature of space. This is an incredibly robust result, confirming with extremely high precision that we live in a flat universe. This finding has a staggering implication that touches on the very nature of reality. A flat universe, in the context of the leading theory of cosmic inflation, suggests that our entire observable cosmos is just a tiny, insignificant patch within a much, much larger and possibly infinite whole. Inflation, the period of hyper-expansion in the first fraction of a second, would have stretched space so dramatically that any initial curvature would have been flattened out, just like inflating a balloon to an immense size makes the surface of any small patch appear flat. If the universe is truly flat and infinite, then what we can see, the 13.8 billion light-year radius of the observable universe, is just our local neighborhood. Beyond our cosmic horizon, space may extend forever, containing an endless number of galaxies, stars, and perhaps even copies of you and me. The flat geometry we measure is our strongest hint that the true scale of all that exists is beyond human comprehension. This revelation about the geometry of the cosmos leads us to a humbling and almost unbelievable fact about its actual composition. We've been talking about galaxies, supernova, and the cosmic microwave background, all made of the familiar atoms and light that we can see and detect. But the stunning truth is that everything we have ever observed with every telescope across every wavelength of light represents a mere sliver of what's actually out there. If we could take a complete inventory of the entire cosmos, the result would be staggering. Only about 5% of the universe is made of the normal matter that constitutes stars, planets, gas, dust, and every one of us. The remaining 95% is composed of two mysterious, invisible entities that we call dark matter and dark energy. Let's start with the component that provides the cosmic scaffolding, dark matter. We've known about its likely existence since the 1930s, when an astronomer named Fritz Zwicky was studying the Coma Cluster, a massive collection of galaxies. He noticed that the individual galaxies within the cluster were moving around at speeds that were far too high. The total gravitational pull from all the visible matter in the cluster, the combined light of all those stars, was simply not enough to hold the cluster together. At those tremendous velocities, the galaxies should have flown apart, scattering into the void. The fact that the cluster remained bound together suggested there had to be a huge amount of unseen mass, a kind of cosmic glue, providing the extra gravity needed to keep everything in place. Zwicky called this missing mass dunkle materie, or dark matter. Since then, evidence for dark matter has piled up from many different directions, making its existence one of the most well-supported ideas in modern cosmology. We see its gravitational effects in the way galaxies rotate. The stars at the outer edges of spiral galaxies orbit just as fast as those near the center, which defies the laws of motion as we understand them. If a galaxy's mass were concentrated in its bright central bulge, those outer stars should be moving much more slowly, like the distant planets in our solar system. The only way to explain their high speeds is if the galaxy is embedded within a vast, massive halo of something that doesn't emit light, a halo of dark matter. We also see its influence through gravitational lensing, where the gravity of a massive object like a galaxy cluster bends the light from even more distant objects behind it. The amount of bending we observe is often far greater than what the visible mass alone can account for, telling us that a huge reservoir of invisible matter is doing the heavy lifting. So what is dark matter? We know it must be something that interacts gravitationally, just like normal matter, which is how it shapes the universe's large-scale structure. But crucially, it does not interact with light or electromagnetic forces at all. It is truly dark. It doesn't absorb, reflect, or emit any form of radiation we can detect. It also seems to not interact with normal matter in any significant way, which is why it can pass right through our planet and us as if we weren't even here. The prevailing theory is that dark matter is some kind of exotic, massive particle that was created in the early universe, a particle that lies completely outside our standard model of particle physics. Decades of experiments deep underground are trying to catch the rare, fleeting interaction of one of these particles, but so far, dark matter has kept its identity a secret, revealing itself only through its profound gravitational influence on the cosmos we can see. Now, add to this mysterious dark matter the even more dominant and bizarre force we discussed earlier, dark energy. Remember, dark energy is not matter at all. It's a property of space itself that causes the expansion of the universe to accelerate. When we combine the evidence, the cosmic budget breaks down like this. Dark energy is the majority shareholder, making up about 68% of the total mass energy content of the universe. Dark matter comes in second at about 27%, and that leaves a mere 5% for everything else, every galaxy, every star, every planet, every living thing. The universe we see when we gaze at the night sky is just the visible froth on the surface of a deep, dark ocean of unknown components. This composition has a direct and dramatic impact on the expansion story. In the early universe, when everything was much closer together, the density of matter, both normal and dark, was very high. Their collective gravity was the dominant force, acting as a brake on the expansion, slowing it down over time. But as the universe grew larger and more diffuse, the matter density dropped. Meanwhile, the energy density of dark energy, being a property of space itself, remained constant. About 5 billion years ago, a cosmic crossover occurred. The universe had expanded enough that the matter density fell below the density of dark energy. At that moment, dark energy became the dominant component, and the expansion of the universe, instead of continuing to slow down, began to accelerate. We are now living in the age of dark energy, an era where the fate of the cosmos is dictated not by the gravitational pull of matter, but by the repulsive push of the vacuum of space. This invisible presence, dark matter, isn't just a passive component of the universe. It plays the absolutely critical role of the cosmic architect, providing the essential gravitational scaffolding upon which everything we see is built. We can think of the luminous universe, the galaxies and stars, as brilliant cities that only exist because they formed within a massive, unseen infrastructure of dark matter. Its gravitational grip is the fundamental force that allowed these structures to form in the first place, and that continues to hold them together against the incredible forces of motion. The evidence for this is overwhelmingly clear when we look at how galaxies behave. Take a classic spiral galaxy like our own Milky Way. The stars in it orbit the galactic center, and by measuring their velocities, we can map out what's called a rotation curve. According to the laws of gravity as defined by Newton and Kepler, stars farther from the center should orbit much more slowly, just as Pluto takes far longer to orbit the Sun than Mercury does. But when astronomers measured these rotation curves, they found something astonishing. The stars out in the distant spiral arms were orbiting just as fast as those near the bright center. This was completely unexpected. If the galaxy's mass were concentrated where the light is, in the central bulge and the inner disk, those outer stars would be moving so fast that the galaxy's gravity wouldn't be strong enough to hold onto them. They should be flung off into intergalactic space. The only plausible explanation is that the visible galaxy is embedded within a much larger, massive halo of something that we cannot see. This halo, made of dark matter, extends far beyond the visible edge of the galaxy. Its gravitational pull is what provides the extra force needed to keep those high-speed outer stars in their orbits. Without this immense, invisible anchor, the galaxy would simply fly apart. The same principle applies on an even grander scale with galaxy clusters. These are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of individual galaxies. The individual galaxies within a cluster are moving relative to each other at tremendous speeds, often thousands of kilometers per second. If you added up the total mass of all the visible stars, gas, and dust in that cluster, the gravity produced would be like a spider web trying to hold together a swarm of speeding bullets. It would be utterly insufficient. The clusters would have evaporated into a diffuse cloud of galaxies eons ago. The fact that they remain intact tells us there must be a huge amount of additional mass, about 5 or 6 times more than the visible matter, binding the cluster together. This missing mass is dark matter, forming a vast, unseen framework that gives the entire cosmic structure its stability. It's the gravitational glue on the largest scales, without which the universe would be a very different and much lonelier place. Now, this cosmic architecture of dark matter leads us to a profound and often misunderstood concept, the very limits of what we can possibly know. We frequently hear that the universe is 13.8 billion years old, which naturally leads to the assumption that we can only see objects up to 13.8 billion light-years away. After all, light travels at a finite speed, so the most distant light we could see should be from objects whose light has been traveling for exactly the age of the universe. But this intuitive picture is incomplete. The reality is far more expansive. The radius of our observable universe is not 13.8 billion light-years, it is a staggering 46.5 billion light-years. How can we see light from an object that, if we could freeze time today, would be nearly 47 billion light-years away, when the universe itself isn't even 14 billion years old? The resolution to this paradox lies in the dynamic nature of space itself. The universe has been expanding during the entire journey of that ancient light. To understand this, let's follow the path of a photon from the most distant galaxy we can observe. That photon was emitted about 13.4 billion years ago, when the universe was very young and extremely compact. At that moment, the galaxy was much closer to us than it is today. The photon began its journey across a relatively small expanse of space, but as the photon traveled through the cosmos, space itself was stretching. It's as if the photon was running on a cosmic treadmill that was constantly lengthening the track ahead of it. The photon was moving toward us at the speed of light through space, but the space between us and the point of emission was relentlessly growing. This means the total distance the photon had to cover to finally reach our telescopes was far greater than the initial distance at the moment it was emitted. By the time that photon arrives at Earth today, having traveled for 13.4 billion years, the galaxy that emitted it is no longer in its original location. The expansion of space has carried that galaxy to a current distance of approximately 46.5 billion light-years away. So, the term observable universe defines a very specific sphere around us. It contains every point in space from which light has had enough time to reach us since the beginning of the universe, accounting for the fact that those points have been moving away from us the entire time due to the expansion of space. The edge of this sphere is not a physical boundary like the edge of a cliff. There is no wall there. Instead, it is a horizon in time, a limit set by the finite speed of light and the relentless stretching of the cosmos. Beyond this cosmological horizon, there are undoubtedly more galaxies, stars, and planets, but their light simply has not had enough time to reach us yet, and because of the accelerating expansion, it never will. This concept of a cosmic horizon leads us to one of the most humbling facts in all of science. The universe we can study, the entire observable cosmos with its 2 trillion galaxies, is almost certainly just a tiny fraction of the whole reality. There is almost certainly a universe beyond what we can ever see, a realm that is forever hidden from our view. This isn't a philosophical idea. It's a direct consequence of the expansion of space and the finite, though incredibly fast, speed of light. Think of it like this: we are on an island in an immense dark ocean. Our telescopes are like powerful lighthouses, but their beams can only reach so far. We can see other islands within the range of our light, but we know the ocean extends far beyond that illuminated circle. In the cosmos, that circle is defined by the distance light has been able to travel in the 13.8 billion years since the universe began. But because space is stretching, the shoreline of our observable island is not static. It's actually shrinking over cosmic time. The reason parts of the universe are becoming permanently invisible is the accelerating expansion driven by dark energy. As space stretches faster and faster, there comes a point for very distant galaxies where the space between us and them is expanding at a rate greater than the speed of light. Now remember, nothing can travel through space faster than light, but space itself can expand at any rate. When this happens, a photon of light emitted from that galaxy toward us will find itself in a hopeless situation. It's like a swimmer trying to cross a river that is widening faster than they can swim. Even though the photon is moving toward us at the ultimate speed limit, the finish line is being dragged away even faster. That light will never arrive. Those galaxies have therefore crossed our cosmological horizon. They have passed from the observable universe into the unobservable. They haven't vanished or been destroyed. They are still there, but their information is forever cut off from us. With every passing moment as the expansion accelerates, more and more galaxies are vanishing over this cosmic horizon, isolating our observable patch from the rest of existence. This leads to a staggering implication about the true scale of everything. The part of the universe we can see, which is already an almost unimaginable 93 billion light-years in diameter, might be just an infinitesimal speck within a totality that is vastly larger or even infinite. The theory of cosmic inflation, which explains the remarkable uniformity of the universe, suggests that the initial exponential expansion didn't just create our observable bubble. It likely created a mind-bogglingly vast landscape. According to this idea, what we call the universe is just one inflating region within a much grander multiverse. Other regions, completely disconnected from our own spacetime, may have stopped inflating at different times, forming their own distinct bubble universes with potentially different physical laws and constants. We are forever separated from these other bubbles by oceans of eternally inflating space that are expanding so rapidly that not even a signal traveling at the speed of light could ever bridge the gap. So what does this mean for our place in the cosmos? It instills a profound sense of humility. Every scientific observation we will ever make, every piece of data we will ever collect, is confined to this one observable patch. Our entire understanding of physics and cosmology is based on a potentially unrepresentative sample. It's as if we were trying to understand the entire Earth by only ever examining a single grain of sand. That grain can tell us a great deal about the composition of sand, but it tells us nothing about oceans, mountains, or continents. Similarly, our observable universe might have certain properties, like the specific value of dark energy, that are unique to our local patch. The fundamental laws we hold as constants might just be the local bylaws of our cosmic neighborhood. This realization doesn't invalidate science, instead it frames our knowledge. It shows that we are embedded within a reality whose full grandeur and complexity may forever lie beyond our grasp, a silent, immense cosmos whose true extent is the ultimate mystery. This accelerating expansion carries a consequence for the far future that is both profound and deeply isolating. The relentless stretching of space doesn't just make distant galaxies harder to see, it actively erases them from the sky one by one. We are living in a uniquely privileged era of cosmic observation. For the first time in history, we have the technology to peer back to the dawn of time, and we still exist at a moment when the light from most of the universe can still reach us. But this golden age of cosmology is fleeting. The same dark energy that is speeding up the expansion is, piece by piece, building an impenetrable wall around our local group of galaxies. Each galaxy that crosses this cosmological horizon doesn't just fade away, it is permanently severed from our future. The light it emits after that point will be fighting a losing battle against the expansion of space itself, which will be carrying the galaxy away faster than its photons can advance toward us. The ultimate fate for any intelligent civilization that arises in this local group trillions of years from now will be one of profound cosmic solitude. Imagine an astronomer on a world orbiting a star in the Andromeda galaxy, which is gravitationally bound to us and will eventually merge with the Milky Way. Billions of years from now, that astronomer will look out into the depths of space and see something utterly different from what we see today. The thousands of galaxies that currently populate our sky will have vanished. First, the most distant ones will have their light redshifted so severely that it slips from visible light into the infrared, then into radio waves, and finally, the wavelength becomes so stretched that the signal is effectively lost in the background noise of the universe. The expansion will have diluted the light of these galaxies to a faint whisper that is impossible to detect, but the isolation goes even deeper than just a darkening sky. For that future civilization, the very evidence for the Big Bang and an expanding universe will have disappeared. The cosmic microwave background radiation, that fossilized echo of creation, will have been redshifted into complete oblivion. Its photons will have been stretched to wavelengths longer than the size of the observable universe itself, rendering them undetectable. The redshift of distant galaxies, the key clue that led us to understand cosmic expansion, will be a phenomenon of the past because there will be no distant galaxies left to observe. The universe, from their limited perspective, will consist of a single merged galaxy floating in an eternal, static, and utterly black void. They would have no way of knowing that the cosmos was ever larger, ever dynamic, or that it had a beginning. The fundamental truths we take for granted today would be completely inaccessible to them. This creates a fascinating and humbling thought experiment. If that future civilization develops the science of cosmology, what story would they tell about the universe? With no evidence of expansion or a hot beginning, they might conclude that the cosmos is eternal and unchanging, consisting only of their own island galaxy. They would be unknowingly trapped in a cosmic cul-de-sac, their science limited by a horizon that hides the true nature of reality. This concept, often called the future blackout or cosmic forgetting, suggests that we live in a special moment not just for life but for knowledge itself. We are positioned at a time when the universe is old enough to have formed planets and life, but still young enough that its history and grand structure remain visible. It underscores that our current understanding of the cosmos is a temporary gift, a window of opportunity that will eventually close as the accelerating universe carries the rest of creation into an inescapable night. Looking ahead to the very end of time, the accelerating expansion we've been discussing sets the stage for several possible ultimate fates for our universe. One of the most dramatic and terrifying scenarios is known as the Big Rip. This isn't just a gradual fading away, it's a violent, catastrophic end driven by dark energy's potential to become infinitely powerful. The key to this fate lies not just in the fact that dark energy is causing acceleration, but in how its properties might change over billions of years. What if the repulsive force of dark energy doesn't remain constant but actually grows stronger as the universe expands? This possibility leads to a chain of events that would unravel the cosmos from the largest scales down to the most fundamental building blocks of matter itself. To understand how this could happen, we need to think about the different scales of structure in the universe and the forces that hold them together. The mightiest structures are galaxy clusters bound by the relentless pull of gravity. Within those clusters are individual galaxies like our Milky Way, which are also held together by gravity. Zoom in further and you have solar systems where a star's gravity keeps planets in orbit. Then there are the planets themselves, held in one piece by their own gravity. Go smaller still, and you find molecules and atoms bound by electromagnetic forces that are incredibly strong over tiny distances. Finally, at the smallest scale, atomic nuclei are held together by the most powerful force in nature, the strong nuclear force. Each of these structures possesses a kind of cosmic glue, a binding energy that resists being pulled apart. The question is, could the expansion of space ever become so powerful that it overcomes even the strongest of these glues? In the Big Rip scenario, the answer is a definitive yes. If dark energy were to intensify into what physicists call phantom energy, the expansion rate of the universe would not just increase, it would accelerate toward infinity over a finite amount of time. Imagine the stretching of space becoming so ferocious that it's no longer a gentle background process. It would transform into an overwhelming force. The first structures to go would be the largest and most weakly bound. Galaxy clusters, those immense cities of galaxies, would be the first to be shredded. The space between the galaxies within a cluster would expand so rapidly that gravity's hold would be broken, sending each galaxy flying off into the ever-growing void, forever isolated. Next, the expansion would turn its attention to the galaxies themselves. The same fate that befell the clusters would happen within a single galaxy like our own. The stars that make up the Milky Way would be torn from their orbits. Our solar system would be flung away from the galactic center, becoming a lonely traveler in an empty darkness. But the horror wouldn't stop there. As the phantom energy continued to intensify, it would attack the solar system. The space between the sun and its planets would stretch with unimaginable force. The gravitational tether holding Earth in its orbit would snap. Our planet would be ripped away from the sun, doomed to drift into the freezing blackness. The catastrophe would then proceed to dismantle Earth itself. The planet's own gravity would be the next victim. The expansion of space would now be happening on a scale smaller than a planet, pulling the very ground beneath our feet apart. Mountains, continents, and eventually every molecule of matter would be subjected to this ultimate force. Molecules would be ripped apart as the electromagnetic forces holding atoms together were overcome. Then, in the final, fleeting moments, atoms themselves would be obliterated. The space between an atom's nucleus and its electrons would be stretched to breaking point, tearing the atom apart. In the last fraction of a second, even atomic nuclei would not be safe. The powerful, strong nuclear force that binds protons and neutrons together would be defeated, and every shred of matter would be dissolved into a diffuse, meaningless cloud of fundamental particles, separated by distances so vast that they could never interact again. The universe would end not with a crunch or a freeze, but with a silent ultimate Chinese letter. Is this our inevitable future? The honest answer is that we don't know. The Big Rip is a speculative scenario based on one particular behavior of dark energy that, so far, our observations have not confirmed. Current data is still consistent with dark energy being a constant force, which would lead to a less violent, though still eternally lonely, fate known as the heat death. The difference hinges on a single number called the equation of state parameter, often denoted as W. If this value is exactly -1, dark energy is constant and the universe expands forever without a rip. If it is less than -1, phantom energy takes hold and the Big Rip becomes a possibility. Our ongoing and future missions, like the Euclid Space Telescope and the Vera C. Rubin Observatory, are designed to measure this parameter with unprecedented precision, hoping to determine which path our cosmos is truly on. While the Big Rip presents a dramatic and violent end, the prevailing theory among cosmologists points toward a far more gradual but equally final destiny known as the heat death or the Big Freeze. This scenario unfolds not with a cataclysmic tear, but with a slow, inexorable fade into darkness and cold, driven by the relentless increase of a concept called entropy. Entropy is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system, like our universe, can never decrease over time. It always increases, moving from a state of order and concentrated energy toward a state of maximum disorder and evenly distributed energy. Think of it like a hot cup of coffee left on a table. Initially, the heat is concentrated in the cup, a state of high order and usable energy. But over time, that heat dissipates into the room, spreading out until the coffee is the same temperature as its surroundings. The energy hasn't vanished, but it has become diffuse and unusable. No work can be done once everything is the same temperature. The universe is undergoing this exact process on a cosmic scale. This journey toward maximum entropy dictates the entire life cycle of the cosmos. Right now, we live in a golden age of structure and energy concentration. Giant clouds of gas collapse under gravity to form stars, which act as immense nuclear furnaces, converting mass into vast amounts of light and heat. Planets orbit these stars, and on at least one, that concentrated stellar energy has fueled the complex chemistry of life. But this era is temporary. As the universe continues to expand and accelerate, the raw materials for new stars, the hydrogen and helium gas scattered between galaxies, will become increasingly scarce. Galaxies will become isolated islands, their gas supplies either used up in star formation or blown away by stellar winds and supernova. One by one, the stars will burn through their fuel. The massive, brilliant blue stars will be the first to go, exploding in spectacular supernova after only a few million years. Smaller stars, like our Sun, will shine for billions of years before swelling into red giants and then collapsing into faint, Earth-sized embers called white dwarfs. The smallest stars, red dwarfs, are the most frugal, potentially shining for trillions of years. But even their immense lifespan is finite. Eventually, the last star in the last galaxy will flicker out, leaving the universe in a state of permanent twilight. The cosmos, however, will not be completely dark yet. For a time, the only sources of light will be the faint glow of white dwarfs and neutron stars as they slowly cool, and the occasional flash when two brown dwarfs or the dead remnants of stars collide. But these events will become rarer and rarer over astronomical timescales. The universe's timeline from this point forward is almost incomprehensibly long. The processes that follow take place over durations that make the current age of the universe seem like the blink of an eye. The next major phase involves the gradual decay of matter itself. According to some theories in particle physics, the protons and neutrons that make up all atomic nuclei may not be truly stable over these vast eons. If certain grand unified theories are correct, protons will eventually decay, with a half-life estimated to be around 10 to the 34 years. That's a 1 with 34 zeros after it. If this occurs, every atom in the universe, every planet, every asteroid, every white dwarf will slowly and silently disintegrate into subatomic particles and radiation. The final structures to hold out against the tide of entropy will be the most gravitationally powerful objects in the universe, black holes, but even they are not eternal. Through a remarkable quantum process at their boundaries known as Hawking radiation, black holes slowly lose mass and energy, evaporating over time. For a stellar mass black hole, this process takes an unimaginably long time, around 10 to the 67 years. For the supermassive black holes at the centers of galaxies, the evaporation time is even more staggering, perhaps 10 to the 100 years. But eventually, even the last black hole will emit its final, faint whisper of radiation and vanish. At this point, trillions upon trillions of years in the future, the universe will have reached its final state. It will be an immense, dark, and nearly empty void. The temperature will approach absolute zero, the point where all molecular motion stops. The last vestiges of energy will be photons of radiation that have been redshifted to incredibly long wavelengths, carrying infinitesimally small amounts of energy, spread perfectly evenly across an infinite and ever-expanding space. This is the heat death, a state of maximum entropy where no energy gradients exist, no work can be done, and no further change of any significance is possible. It is a quiet, cold, and eternal equilibrium, the ultimate fate of a universe that has expended all of its potential for structure, complexity, and life. This journey into the far future reveals a cosmos destined for stillness, but it also compels us to look back to the very beginning, to a mechanism so powerful it may have created not just our universe but a multitude of them. The theory that best explains the properties of our universe, its large-scale flatness, its uniformity, is cosmic inflation. This idea proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating from smaller than a proton to a macroscopic size in an almost unimaginably brief instant. This inflation smoothed out the cosmos and set the stage for the more gradual expansion we see today. But a fascinating implication of many inflationary models is that this process might not have been a one-time event. Instead, inflation could be eternal, a process that started in some primordial patch and continues to create new universe bubbles forever. Think of it like a cosmic volcano that is constantly erupting. Our entire observable universe is just one bubble of cooled lava that formed on the side of that volcano. But the eruption itself never stops. In other regions of this eternally inflating landscape, new bubbles of space-time are continuously popping into existence, each undergoing its own rapid inflation before settling down into a more sedate expansion. Each of these bubbles would constitute a separate universe disconnected from our own, with its own distinct Big Bang and its own subsequent history. This vast and possibly infinite collection of universes is what scientists refer to as the multiverse. Our expanding cosmos, with its specific laws of physics and constants, would then be just a single specimen in an unimaginably vast cosmic zoo. What makes this idea truly staggering is the possibility that the fundamental laws of nature might not be as fundamental as we think. In our universe, we have measured constants like the strength of gravity, the mass of an electron, or the value of dark energy. These numbers seem finely tuned. If they were even slightly different, stars wouldn't form, complex chemistry would be impossible, and life could not exist. This fine-tuning puzzle has long perplexed scientists and philosophers. The multiverse offers a compelling, if speculative, solution. If there are an infinite number of universes, each with a random set of physical constants, then it's no surprise that we find ourselves in one where the numbers are just right for our existence. We couldn't have arisen in a universe where the laws prohibit galaxies, stars, or planets. In this view, the strange suitability of our cosmos for life is not a miracle. It is a selection effect, often called the anthropic principle. We are simply living in one of the rare habitable bubbles in a vast cosmic landscape that is mostly barren and hostile. This concept pushes the boundaries of science itself. By its very nature, these other universes would be causally disconnected from ours. No signal, not even light, could ever cross the inflationary gulf between them. This means the multiverse might be inherently unobservable. moving it from the realm of direct experimental verification into the domain of theoretical physics and philosophy. However, its appeal lies in its power to provide a natural explanation for the deepest puzzles of our own universe. The inexplicably small but non-zero value of dark energy, for instance, could simply be a random roll of the cosmic dice in our particular bubble. While we may never be able to point a telescope at another universe, the multiverse theory encourages us to see our own cosmic home in a new light, not as the entire reality, but as one unique expression of physics within a much grander and perhaps infinite meta-reality. To fully grasp the power of cosmic expansion, we need to rewind the cosmic film not just to the first galaxies or the release of the cosmic microwave background, but all the way back to the very beginning. And when we do, we arrive at a fact that is arguably the most astounding of all. There was a moment when the entire observable universe, all of space and everything it would ever contain, was smaller than a single atom. This is the ultimate implication of the Big Bang. If the universe is expanding today, then yesterday it was slightly smaller. A billion years ago, it was significantly more compact. As we continue to reverse the flow of time, the galaxies crowd together, the temperature soars, and all the matter and energy we see distributed across billions of light years converges into an increasingly tiny, incredibly dense, and unimaginably hot point. This state is what cosmologists call a singularity, a point of infinite density and temperature where the known laws of physics as we understand them simply break down. This journey backward is a descent into extremes. Let's start from a time we can somewhat comprehend, about 380,000 years after the beginning, when the universe became transparent and the cosmic microwave background was released. At that point, the entire cosmos was a hot plasma, roughly the temperature of the surface of the Sun, and it was already vast but still far more dense than today. Now, let's rewind further to just 1 second after the Big Bang. The universe is now so hot and dense that atomic nuclei cannot even hold together. It's a seething soup of fundamental particles like protons, neutrons, and electrons. Go back to just 1 microsecond, 1/1,000,000th of a second, and the energy is so intense that even protons and neutrons dissolve into their constituent parts, a roiling ocean of quarks and gluons. The conditions are more extreme than those inside the largest particle colliders we can build, but to approach the true beginning, we must venture into the first minuscule fractions of a second. At 10 to the power of -32 seconds, that's a decimal point followed by 31 zeros, and then a 1. The universe was undergoing the phenomenally rapid expansion of inflation. And just before that period, the entire observable universe was compressed into a region of space smaller than a proton. Its temperature was astronomically high, beyond any number we can easily relate to. All the forces of nature, gravity, electromagnetism, and the nuclear forces were likely unified into a single primordial force. In this state, the distinction between matter and energy blurred, governed by the wild rules of quantum gravity, a theory that still eludes our complete understanding. This was not just a small, hot ball of gas. It was the entirety of spatial reality confined to a scale so tiny it defies human intuition. Every galaxy, every star, every planet, and every person was encoded in the potential of that infinitesimal point. Trying to visualize this is a profound challenge. It's not like a tiny seed that existed within a larger, empty space. That is a critical distinction. According to our best models, space itself did not exist around this primordial speck. The singularity was space. There was no outside. The entire universe, all that exists, was contained within that single point. The Big Bang, therefore, was not an explosion into pre-existing space like a firecracker going off in a room. It was the rapid expansion of space itself, starting from that initial state. It was the sudden, dramatic unfurling of the very fabric of the cosmos from an unimaginably condensed beginning. This is why we say the universe has no center, because the Big Bang happened everywhere at once, as every point in our current universe was once overlapping in that same initial singularity. This concept pushes the limits of our physics. The conditions of such extreme density and temperature are so foreign that Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe so well, cannot cope. At the singularity, the equations of relativity predict infinite values, which is a clear signal that the theory is incomplete. To understand the true moment of creation, we need a theory that can marry general relativity with quantum mechanics, a theory of quantum gravity. This is the holy grail of modern physics, and candidates like string theory or loop quantum gravity attempt to describe what might have happened. Some of these theories suggest that there was no true singularity at all, but rather a bounce from a previous contracting universe or a quantum foam where time and space lost their conventional meaning. What remains undeniable, however, is the observational evidence that points back to this hot, dense origin. The expansion we see, the cosmic microwave background, and the abundance of light elements all form a consistent story that leads us back to a beginning where the universe was, for all practical purposes, smaller than an atom, a seed containing the entire potential for everything we see today. The cosmic story from that primordial seed doesn't just involve the expansion of space. It also chronicles the very moment when the first building blocks of matter were forged. After the initial, incomprehensible moments of the Big Bang, the universe began to cool as it expanded. By the time it was just 1 second old, it had cooled enough for the fundamental particles to start settling into stable structures. This set the stage for a remarkably brief but incredibly productive period known as Big Bang nucleosynthesis, a 3-minute window where the universe acted as the first and largest nuclear fusion reactor, creating the lightest elements that would become the raw material for everything to come. During this era, the cosmos was a seething, opaque plasma, far too hot for atoms to exist. The universe was filled with a dense soup of fundamental particles, protons, neutrons, electrons, and photons of light, all constantly colliding with immense energy. Protons, which are simply hydrogen nuclei, were the most abundant. But as the temperature plummeted from trillions of degrees, a crucial change occurred. Neutrons, which are unstable on their own, began to fuse with protons. The first and simplest fusion reaction created deuterium, a heavy isotope of hydrogen consisting of 1 proton and 1 neutron. This was a critical bottleneck. If the universe had expanded and cooled too quickly, even this simple step might not have happened, leaving us with a cosmos of pure hydrogen. But the conditions were just right. Once deuterium nuclei formed, they could rapidly collide with more protons and neutrons to form the next element in the chain, helium. The entire process was a frantic race against the clock of the expanding universe. As space stretched, the density and temperature of the particle soup dropped rapidly. Within about 3 to 4 minutes, the universe had cooled and thinned so much that the average energy of particle collisions fell below the threshold needed for nuclear fusion to continue. The window for element building slammed shut. In that incredibly short time, the cosmos accomplished a fundamental task. It transformed about 25% of the ordinary matter in the universe by mass from simple hydrogen into helium-4, the most common isotope of helium. Trace amounts of other light elements were also produced, including a tiny fraction of lithium and an even smaller amount of helium-3. And then, for the next several 100 million years, nothing else happened. The universe was too diffuse for any further fusion until gravity could eventually pull matter together to form the first stars. The most compelling evidence for this ancient forging process is all around us, or rather, above us. When astronomers measure the chemical composition of the oldest stars in our galaxy and of pristine gas clouds in intergalactic space, they find a consistent and remarkable ratio. No matter where they look, the oldest observable material in the universe is about 75% hydrogen and 25% helium by mass. This universal abundance is a powerful prediction of Big Bang nucleosynthesis. Stars themselves fuse hydrogen into helium throughout their lives, and in their deaths they create heavier elements like carbon and oxygen. But no stellar process could have produced such a uniform, widespread distribution of helium. The only explanation is that this helium was present from the very beginning, a relic of that frenetic 3-minute period when the entire universe was a single, unified fusion furnace. This precise agreement between theoretical prediction and observational measurement is one of the 3 great pillars of evidence for the Big Bang, standing alongside the expansion of the universe and the existence of the cosmic microwave background. It confirms that our understanding of physics can reliably trace the history of the cosmos back to its earliest moments. After the universe cooled and became transparent, releasing the cosmic microwave background, it entered a long, dark era. For hundreds of millions of years, the cosmos was a vast, shadowy realm filled with a fog of neutral hydrogen and helium gas. There were no stars, no galaxies, and no sources of light. This period is aptly named the Cosmic Dark Ages. The universe was a simple, quiet, and profoundly dark place. But this darkness was not permanent. It was merely the calm before a storm of cosmic creation. The seeds for this transformation were already present in the tiny density fluctuations imprinted in the cosmic microwave background. Over eons, gravity patiently worked on these slight irregularities, pulling denser regions of dark matter and gas together. Slowly, the first protogalactic clouds began to condense, and within them, the very first stars were born. Their ignition did not just bring light. It fundamentally and permanently altered the nature of the cosmos itself, heralding the start of a pivotal chapter known as the epoch of reionization. These first stars, often called population 3 stars, were unlike anything that exists today. Formed from the pristine, pure hydrogen and helium left over from the Big Bang, they lacked the heavier elements that help modern stars regulate their size and temperature. As a result, they were behemoths thought to be hundreds of times more massive than our Sun. And with immense mass comes immense power. These stellar titans burned ferociously hot and bright, emitting enormous amounts of energetic ultraviolet radiation. Their lives were spectacularly short, ending in titanic supernova explosions after only a few million years. But in their brief existence, they unleashed a flood of ultraviolet photons into the surrounding space. This radiation held the key to changing the universe from an opaque fog back into the transparent void we know today. To understand this transformation, we need to revisit the state of the universe after the Dark Ages. The hydrogen gas filling space was neutral, meaning each hydrogen atom had its single electron bound to its proton. This neutral hydrogen gas is very efficient at absorbing ultraviolet light. So when the first stars switched on, their intense UV radiation didn't travel far. Instead, it began to strike the surrounding neutral hydrogen atoms. Each UV photon carried enough energy to rip the electron away from its proton, a process known as ionization. Think of it as a cosmic battle between light and fog. The stars were like lighthouses, and their UV beams were slowly burning away the dense fog around them, creating ever-growing bubbles of transparent, ionized plasma, a plasma where electrons and protons were separated and could not easily recombine. As more stars ignited, and as the first galaxies began to coalesce, these bubbles of ionized gas grew larger and started to overlap. This was not a gentle process, it was a cosmic upheaval. Over several 100 million years, these bubbles of ionized gas merged, creating a vast, interconnected network of transparency. The epoch of reionization was the period when the universe-wide fog of neutral hydrogen was systematically blasted apart by the cumulative radiation from the first generations of stars and galaxies. By the time the universe was about 1 billion years old, the job was largely complete. The intergalactic medium had been permanently transformed from a neutral state back into an ionized plasma, just as it had been before the release of the cosmic microwave background, but now at a much lower density. This reionization made the universe transparent to most wavelengths of light, allowing the light from all subsequent generations of stars and galaxies to travel across vast cosmic distances without being absorbed, which is why our modern telescopes can peer so deep into the cosmos. The evidence for this great reionization event is etched into the light of the most distant objects we can observe. When astronomers study quasars, incredibly bright cores of active galaxies that are billions of light years away, they see a telltale signature in their spectra. At a certain point corresponding to a look-back time of over 13 billion years, the light from these quasars shows a complete absorption of specific wavelengths that are characteristic of neutral hydrogen. This phenomenon, known as the Gunn-Peterson trough, indicates that at that early epoch, the light was passing through a universe still filled with a significant amount of neutral fog. For quasars that are closer to us and therefore from a later time, this trough disappears, indicating that the fog has been cleared. This observational evidence strongly supports the narrative of a universe that was once opaque and then was permanently reionized by the first brilliant sources of light, opening up the cosmos for all the starlight that was yet to come. The expansion of the universe and the violent events of its birth didn't just create particles and light, they also sent tremors through the very fabric of reality itself. These tremors are known as gravitational waves, and their existence was one of the most astonishing predictions of Einstein's theory of general relativity. Einstein showed that gravity is not a mysterious force reaching across space, but rather a curvature of spacetime caused by mass and energy. Picture a rubber sheet stretched taut. A heavy ball placed in the center creates a dip. This is analogous to how the Sun warps the space around it, causing the Earth to orbit along the curved geometry. But Einstein's equations revealed something even more dynamic. When massive objects accelerate, particularly when they undergo cataclysmic violence like the collision of two black holes, they can create ripples in this spacetime fabric. These ripples are gravitational waves. They travel outward at the speed of light, stretching and squeezing space itself in a perpendicular pattern as they pass by. For decades, these waves were purely theoretical, as their effect is infinitesimally small. Detecting them required witnessing the most energetic events in the cosmos. The first direct detection of gravitational waves in 2015 by the LIGO Observatory was a monumental achievement, confirming a century-old prediction and opening an entirely new window on the universe. It allowed us to hear the collision of black holes, events that emit no light whatsoever. But the gravitational waves LIGO detects are like the crashing of individual ocean waves, loud, distinct events from specific cosmic catastrophes happening in the relatively recent universe. There is another, far more subtle and ancient type of gravitational wave that scientists are desperately trying to find. A background hum of primordial gravitational waves generated in the first fleeting moments after the Big Bang. This would be the faint cosmic echo of creation itself. The leading candidate for generating these waves is the same process that explains the universe's large-scale smoothness, cosmic inflation. This period of hyper-expansion, when the universe doubled in size countless times in a fraction of a second, would have been an incredibly violent process. The rapid, exponential stretching of spacetime would have been chaotic, churning the fabric of the cosmos and generating a cacophony of spacetime ripples that would have permeated the entire universe. This primordial gravitational wave background is not just a curiosity, it is a potential portal to a time far earlier than we can see with light. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old. But these gravitational waves would have been generated in the first trillionth of a trillionth of a trillionth of a second. carrying information from an epoch that is completely inaccessible by any other means. Detecting them would be the strongest possible evidence for inflation and would provide crucial clues about the energy scales at which it occurred, potentially revealing connections to the fundamental forces of particle physics. The primary method for hunting this signal involves searching for its unique imprint on the cosmic microwave background. As these primordial ripples passed through the hot, dense plasma of the early universe, they would have subtly polarized the light, creating a distinctive swirling pattern in the CMB's polarization known as a B-mode signal. Finding this specific fingerprint is one of the highest goals in modern cosmology. Experiments like the BICEP and Keck array telescopes at the South Pole and future space-based observatories are tirelessly scanning the CMB for this faint signature. The hunt is extraordinarily difficult as the signal is incredibly weak and can be easily confused with polarization caused by interstellar dust within our own galaxy. While a claimed detection in 2014 was later shown to be mostly due to this dust, the search continues with ever more sensitive instruments. Successfully detecting these primordial ripples would not just confirm a theory, it would allow us to probe the universe at energies 1 trillion times higher than what the Large Hadron Collider can achieve. It would be like listening to the faintest whisper from the instant of creation, a direct message from the very birth of spacetime, offering a glimpse into the fundamental laws that govern all of existence. Now, while we've been discussing the grand, uniform expansion of the universe, it's crucial to understand that this is the average behavior on the very largest scales. When we zoom in closer to home, the story gets more complex and far more interesting. On the scale of individual galaxy clusters and superclusters, the relentless pull of gravity can create powerful local currents that dramatically override the general cosmic expansion. This brings us to one of the most intriguing cosmic mysteries in our own backyard, the Great Attractor. Observations reveal that our entire local group of galaxies, including the Milky Way, is not simply drifting apart with the Hubble flow. Instead, we are on a collision course with our giant neighbor, the Andromeda Galaxy, and both of our galaxies, along with dozens of others, are all being pulled in the same direction by a force far greater than our own. This collective motion was first discovered in the 1970s and 80s. Astronomers were mapping the velocities of galaxies in our vicinity relative to the smooth expansion predicted by Hubble's law. They expected to see small, random deviations like boats bobbing on a gently swelling ocean. What they found was anything but random. Our entire local region of space, encompassing millions of light years, is flowing like a river toward a specific point in the sky, in the direction of the southern constellations Centaurus and Norma. This mysterious, massive concentration of gravity was dubbed the Great Attractor. It's as if we are all sliding down a gentle but immense slope in the fabric of spacetime, drawn toward a hidden valley of immense mass. For a long time, the nature of the Great Attractor remained elusive because it happens to lie directly behind the plane of our own Milky Way galaxy. This region is known as the zone of avoidance, where our view of the distant cosmos is obscured by thick clouds of interstellar gas and dust and the dazzling density of stars in the galactic disk. It's like trying to see a distant mountain range through a dense fog. Early observations could only sense its gravitational influence by the motion of galaxies around it, but direct observation was a tremendous challenge. We knew something massive was there, pulling us toward it at a staggering speed of over 600 kilometers per second, but we couldn't clearly see what it was. The mystery deepened with further study. As our observational tools improved, particularly with infrared and radio telescopes that can peer through the galactic dust, astronomers began to map the structure behind the Great Attractor. They discovered that the Great Attractor itself is not the final destination, but rather a waypoint on a much longer journey. The pull we feel is part of an even larger flow, carrying our local group and the entire Virgo supercluster toward an unimaginably vast conglomeration of matter known as the Shapley supercluster, one of the largest known structures in the observable universe. The Great Attractor, it turns out, is likely the core of our own local supercluster, which has been named Laniakea, a Hawaiian word meaning immeasurable heaven. This discovery redefined our cosmic address, showing that we are part of a sprawling web of galaxies stretching over 500 million light-years, all interconnected by gravity's invisible threads. So, what exactly is the Great Attractor? It is not a single, monstrous object, but the gravitational center of mass of the Laniakea supercluster. This region contains the mass of tens of thousands of galaxies, a concentration so immense that its gravity dominates the expansion of space in our local volume of the cosmos. This resolves the paradox beautifully. The Great Attractor isn't an anomaly that breaks the rules of cosmic expansion. Instead, it is a stunning demonstration of how gravity works on different scales. The expansion of space is the dominant force in the great voids between superclusters where matter is sparse. But within the dense walls and nodes of the cosmic web, gravity is king. The collective pull of all that mass creates a gravitational well so deep that it can bring galaxies together, even as the universe as a whole continues to expand. The Great Attractor is a powerful reminder that we live in a structured universe where we are part of a celestial watershed, flowing along gravitational currents toward the dense heart of our local supercluster. Now, just when we think we have a coherent picture of a smooth, uniform, and statistically random early universe, the cosmos throws us another curveball, one so peculiar it's been given a rather dramatic name: the axis of evil. This isn't a malevolent force, but a mysterious and controversial pattern found etched into the most pristine data we have, the cosmic microwave background. Recall that the CMB is meant to be the ultimate snapshot of the infant cosmos, a nearly perfect blackbody radiation field with tiny, random temperature fluctuations that served as the seeds for all future structure. The standard cosmological model assumes these fluctuations should be evenly distributed, with no preferred direction or special axis. They should be isotropic, looking statistically the same no matter which way you gaze into the depths of space. But when scientists analyzed the incredibly detailed maps from the WMAP and later the Planck satellites, they noticed something that sent a ripple of unease through the cosmology community. The largest scale fluctuations, the biggest waves in the early universe, appear to be subtly aligned along a particular axis in the sky. It's as if the universe has a preferred direction, a cosmic fingerprint that challenges the very foundation of the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. To understand why this is so strange, imagine you're standing in the middle of a vast, empty field during a light snowfall. The snowflakes should fall around you with a beautiful randomness, landing equally in all directions without any pattern. This is what we expect from the CMB. The axis of evil, however, is like discovering that all the largest snowflakes are falling in a way that aligns along a single line running through you. It doesn't affect the small-scale details, the individual flakes, but the overall arrangement of the biggest one seems to have a curious order. In technical terms, the quadrupole and octupole moments of the CMB, which describe the very largest patterns of hot and cold spots, show a surprising degree of correlation and alignment along this axis. This unexpected coherence suggests that the universe might not be as directionless as we've always assumed. The axis itself runs through the constellations of Virgo and Hydra, and strangely, it also appears to be aligned with the plane of our solar system and the direction of the sun's motion through space, a correlation that makes some scientists deeply suspicious that we might be seeing some unknown local contamination or an unaccounted-for systematic error. Naturally, such a provocative finding has sparked a wide range of interpretations. The most conservative and perhaps most likely explanation is that this is simply a statistical fluke. When you analyze a massive dataset with millions of data points, you're bound to find some odd-looking patterns purely by chance. It's the cosmic equivalent of seeing a face in the clouds. Our brains are wired to find patterns even where none exist. Proponents of this view argue that the significance of the alignment is marginal, and that as we collect more data from future missions, the anomaly will probably fade into insignificance, just a curious footnote in the history of cosmology. However, the persistence of the signal across different satellite missions has kept the door open for more exotic possibilities. Some theorists have proposed that the axis of evil could be a genuine window into physics beyond our standard model. One fascinating, though highly speculative, idea is that it represents an imprint of a pre-Big Bang reality. If our universe was born from a collision with another universe in a multiverse landscape, or if it inherited a preferred direction from an earlier phase of existence, that primordial structure could have left a faint trace on the fabric of space-time, visible only on the very largest scales. Another possibility is that it hints at a flaw in our understanding of inflation, the period of hyper-expansion that is supposed to have wiped clean any such primordial preferences. Perhaps inflation did not last quite long enough to completely randomize everything, leaving behind a ghost of a previous order. While these ideas are far from mainstream, they highlight how a single, stubborn anomaly can push scientists to consider realms of physics we never thought to explore, reminding us that our most cherished models are always subject to revision by the next surprising observation. While the vast cosmic structures we've explored, superclusters, dark matter halos, and galaxy filaments paint a picture of a crowded universe, this impression is a grand illusion. The overwhelming reality, which the expansion of space exploits so effectively, is that the cosmos is almost entirely a void of unimaginable emptiness. To truly grasp the scale of this nothingness, consider our own solar neighborhood. We often picture the solar system as a relatively compact family of planets orbiting the Sun. Yet the distances are so vast that they defy everyday intuition. If you were to shrink the Sun down to the size of a marble about 1 centimeter in diameter, the Earth would be another marble about 1 meter away. But on this scale, the next nearest star, Proxima Centauri, would be located over 260 kilometers away. That's the equivalent of placing 2 marbles in 2 different cities, with absolutely nothing but empty space between them. This profound isolation only intensifies as we zoom out. A galaxy like our Milky Way, containing an estimated 100 to 400 billion stars, seems like a teeming metropolis. But its diameter is so immense, about 100,000 light-years, that the average distance between stars is still about 5 light-years. That's over 40 trillion kilometers of near-total vacuum separating each stellar island. The galaxy is less a dense swarm and more a collection of faint fireflies scattered across a continent-sized dark room. Even within this sparse distribution, the stars and their planets represent the densest knots of matter. The space between them is filled with the interstellar medium, a gas so thin that its best laboratory vacuum on Earth would be considered dense by comparison. A single teaspoon of what we call a hard vacuum on Earth contains more atoms than a teaspoon of the average space between stars. This staggering emptiness is the fundamental stage upon which the drama of cosmic expansion unfolds. The stretching of space isn't happening against a resistant medium. It is amplifying the gaps that already exist. The universe is not like an inflating balloon filled with air. It is more like an inflating balloon whose surface is dotted with a few specks of dust that are already miles apart. The expansion simply makes those miles become tens of miles, then hundreds. This is why the expansion is so dominant on the largest scales. In the great voids between galaxy clusters, where matter is at its most sparse, the subtle repulsive force of dark energy faces little opposition from gravity's pull. It is in these near-perfect vacuums, these cosmic deserts spanning hundreds of millions of light-years, that dark energy finds its greatest leverage, relentlessly pushing the walls of the cosmic web further and further apart. The increasing isolation of galaxies is not a minor side effect. It is the direct and inevitable consequence of stretching an already almost empty cosmos. We are witnessing the dilution of reality itself as the already tiny islands of matter are carried ever farther into the deepening night. To truly grasp the distances we've been discussing, like the size of the observable universe or how far away a galaxy is, we need to introduce one of the most crucial yet subtle tools in a cosmologist's toolkit, the concept of co-moving distance. You see, measuring distance in an expanding universe is far more complicated than it seems. It's not like measuring the fixed distance between two cities on a map. Because space itself is stretching, the distance between any 2 points that are not gravitationally bound is constantly increasing. This creates a fundamental challenge. When we say a galaxy is, for example, 13 billion light-years away, what exactly do we mean? Is that how far it was when the light left, or how far it is right now? To resolve this, cosmologists use two distinct ways of thinking about cosmic distance, and understanding the difference is key to seeing the universe clearly. The first, more intuitive concept is called proper distance. This is the actual, physical distance between two objects at a specific moment in cosmic time. Imagine you could freeze the expansion of the universe right now, and then lay out a giant, rigid ruler from Earth to that distant galaxy. The measurement you would read on that ruler is the proper distance at this exact instant. It's a snapshot of the separation at a single moment. However, because the universe is expanding, this number is a moving target. If you were to take another snapshot 1,000,000 years from now, the proper distance would be larger, even though neither object has moved through space on its own. The stretching of the fabric between them has increased the separation. This is the distance that is effectively growing due to the Hubble flow, the general expansion of space. Now here's where co-moving distance comes in. Think of it as a cosmic accounting trick that removes the confusing effect of expansion. A co-moving distance is a measure that remains constant over time. It factors out the stretching of space, allowing us to track an object's position within the expanding coordinate system of the universe itself. The best way to visualize this is to go back to our classic analogy of the expanding raisin bread. Imagine that each raisin has a set of co-moving coordinates baked right into the dough around it. As the bread rises, the raisins move apart because the dough between them expands. The proper distance between any two raisins increases, but their co-moving coordinates stay the same because they are fixed to their local patch of dough. The co-moving distance is a way of saying, forget about the expanding dough for a minute. In the coordinate system of the bread itself, these two raisins have always been this many bread units apart. This distinction resolves the paradox we mentioned earlier about the observable universe being 93 billion light-years in diameter, even though the universe is only 13.8 billion years old. The light from the most distant galaxies has been traveling for about 13.4 billion years. The co-moving distance to that galaxy's location when it emitted the light was very small. But during the billions of years the light was in transit, the space it was traveling through expanded enormously. By the time the light reaches us, the proper distance to that galaxy, the distance now, has grown to around 46.5 billion light-years. The radius is that, so the diameter is twice that, hence the 93 billion light-year figure. The co-moving distance gives us a stable frame of reference to understand where that galaxy truly resides in the cosmic web, while the proper distance tells us how much empty space has been generated between us since the light began its journey. This framework is not just a philosophical exercise, it's the bedrock of modern cosmology and how we interpret our observations. When astronomers publish a catalogue of galaxies, the distances listed are almost always co-moving distances. This allows scientists to map the large-scale structure of the universe. the filaments, walls, and voids without that map becoming instantly outdated as the universe expands. It's like using a grid that expands with the universe, so every object keeps its grid position forever. This makes it possible to study the distribution of matter and the growth of structure over cosmic time. Furthermore, the relationship between redshift, which we can measure directly from a galaxy's light, and distance is defined using the co-moving distance. This is why the Hubble constant, the current expansion rate, is so critical. It is the conversion factor that translates a co-moving distance into a velocity of recession. By mastering these two ways of measuring, we can accurately navigate the past, present, and future of our ever-growing cosmos, separating the motion of objects through space from the relentless stretching of space itself. And so we arrive at the final and perhaps most beautiful fact of all, one that connects the grand cosmic narrative directly to our own existence. Every atom in our bodies, every element that makes life possible, was forged in the heart of a star that lived and died long before our sun was even a glimmer in the cosmos. We are, in the most literal sense, made of stardust. This profound connection imbues the expansion of the universe with a deeply personal and poignant meaning, transforming it from a distant physical phenomenon into a story about our own origins and our ultimate place in the vastness of space and time. To understand this, we must follow the epic journey of matter. In the very beginning, after the Big Bang, the universe contained only the simplest elements: hydrogen, helium, and a trace of lithium. These are the building blocks, but they are not enough to build a planet like Earth, let alone a living organism. Life as we know it requires a rich chemical palette: carbon, nitrogen, oxygen, phosphorus, and iron, to name just a few. These heavier elements are created only under the most extreme conditions, the intense pressure and heat at the core of a massive star. For millions of years, a star like this fuses hydrogen into helium, but as it nears the end of its life, it begins to fuse heavier and heavier elements, creating a layered onion-like structure with iron at its core. This process cannot continue indefinitely. The formation of iron actually consumes energy instead of releasing it, causing the star's furnace to sputter and die. Without the outward pressure from fusion, the star's own immense gravity causes it to collapse in on itself in a cataclysmic explosion known as a supernova. It is in this final, violent act of stellar death that the true magic happens. The incredible energy of a supernova is enough to forge all the elements heavier than iron, from gold and silver to uranium. The explosion then hurls this newly created, enriched material far out into the surrounding interstellar space, seeding the cosmic clouds with the ingredients for new stars, planets, and life. Our solar system formed from just such a cloud, a nebula enriched by the ashes of countless generations of stars that lived and died over billions of years. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once part of a star that met a spectacular end. We are the universe become conscious, a way for the cosmos to look back on itself and contemplate its own history. This intimate connection makes the expansion of the universe feel strangely personal. The very stars that created us are now being carried away by the stretching of space. The stellar nurseries, the great spiral galaxies where new suns are born from the recycled remains of the old, are receding into the distance. With each passing moment, the cosmic environment that gave rise to us becomes more remote. We are living on an island that is slowly watching the continent drift away. This creates a profound sense of cosmic loneliness, a realization that the conditions that led to our existence were a unique and temporary alignment in an ever-changing cosmos. The universe provided the crucible for life, but it is not a static home. It is a dynamic, expanding stage that is gradually dismantling the very scenery that made the play possible. Yet there is also a triumphant beauty in this narrative. For a brief moment in cosmic time, we are here. We have emerged from the dust of exploded stars, and we have developed the capacity to understand this incredible story. We can trace our lineage back through the supernova, through the formation of the solar system, through the evolution of life on Earth, to this present moment where we can look up at the night sky and comprehend our origins. The expansion of the universe, which will ultimately lead to isolation and darkness, is the very same process that has given us this window of opportunity for knowledge and wonder. We are living in a golden age, a time when the universe is still young enough for its history to be readable, and we are conscious enough to read it. The stars are drifting away, but their light has already reached us, carrying the message of our own stellar ancestry. We are a fleeting but meaningful part of a grand, ongoing cosmic evolution, a whisper of awareness in the immense and silent expanse. So as we've journeyed through these 25 astounding facts, a single, transformative truth emerges. Our universe is not merely a vast, static stage upon which events unfold. It is a dynamic, living entity, actively expanding and accelerating in a cosmic drama of unimaginable scale. From the initial, brilliant flash of the Big Bang, when all of reality was compressed into a space smaller than an atom, to the relentless stretching driven by the mysterious force of dark energy, we are participants in an ongoing creation story. The very fabric of space is growing, carrying galaxies away from one another and reshaping the future of everything we know. This isn't a distant concept, it is the fundamental context of our existence, the backdrop against which every star is born and every planet forms. The implications of this expansion ripple through our understanding of time, reality, and our own place within it. It rewrites the story of our origins, pointing back to a definite beginning and providing the mechanism that turned quantum fluctuations into the majestic cosmic web of galaxies we see today. It forces us to confront a future that is anything but stable, a destiny that could lead to the ultimate isolation of a heat death or the violent dissolution of a big rip. Perhaps most humbling of all, it reveals that the world we perceive, filled with stars and planets, is just the visible 5% of a cosmos dominated by completely unknown components, dark matter and dark energy. We are left with the staggering realization that we have only begun to map the true nature of reality. This journey underscores a profound and beautiful paradox. The same cosmic forces that will eventually lead to a cold, dark, and empty future are the very same forces that made our existence possible. The expansion allowed the universe to cool and structure to form. The death of massive stars in spectacular supernova, events set in motion within these evolving galaxies, forged the heavy elements that constitute our bodies and our world. We are literally children of the stars, living in a fleeting golden age where the universe is old enough to have created us, yet young enough that its history remains visible to our telescopes. Our ability to comprehend this grand narrative is a precious and temporary gift, a spark of awareness in the immense cosmic night. The exploration of these mysteries is far from over. The Hubble tension, the nature of dark energy, and the search for primordial gravitational waves are the frontiers of modern cosmology. Each unanswered question is an invitation to delve deeper, to question our assumptions, and to expand our knowledge. The universe continues to surprise us, challenging us to think bigger and to appreciate the incredible complexity of the cosmos we call home. This isn't the end of the story, it is an ongoing invitation to curiosity and wonder. Now, we'd love to hear from you. Which of these 25 facts about the expanding universe left you the most amazed? Was it the concept of the observable universe being 93 billion light-years wide, the idea that we may be part of a multiverse, or the haunting future where the evidence for the Big Bang itself will vanish? Share your thoughts in the comments below. Let's continue this conversation about the greatest story ever told. If you enjoyed this journey to the edge of understanding, please subscribe to the channel for more deep dives into the mysteries of space, time, and reality. Thank you for watching.